I'm Nancy Beck from the board of Princeton Adult School. Now, let's get on with what we came here for. If you read your brochure, you know that we planned this series in memory of Aaron Lemenick, who was, among other things, in his retirement, a hardworking member of the Princeton Adult School Board. We are delighted that Aaron's son, Michael Lemenick, is here to introduce both the series and tonight's speaker. Now, I'm not going to introduce the introducer, other than to say that Michael is senior science writer for Time Magazine. Mike.
Just hold this thing. Thank you. If my father were here tonight, by the way, I've been asked to do this introduction partly because the series is named for my father, but partly because everyone tells me I look like him. So you're going to pretend it's him up here. We're going to talk. If my father were here tonight, he would have been whispering in my ear just before I came up here his two cardinal rules for introducers. And there were two things. He said, always be brief and then be seated. And I'm going to do that because the series itself is what you're here for, and it's going to be wonderful. But I've been asked to say just a couple of words about my father and then to introduce tonight's speaker. My father would have been thrilled and honored and overwhelmed to have this series named after him for a number of reasons. First of all, he fell absolutely in love with Princeton when he first arrived here in 1950. And when he came back in 1961 to join the faculty, he never wanted to leave again, and he never did. And what he also did around that time, in 1950, a little before that, was to fall hopelessly in love with physics. The idea for him that we human beings, who all have just sort of the basic equipment, somehow have managed to learn as much as we have about the universe. He loved it. And he loved, even more, telling this to everybody else. He loved to teach above all. And that is why, after many people thought he had retired and disappeared, he served on the board of the Princeton Adult School. He taught in the teacher preparation program at the university in the summer. He tutored at the high school. He could not get enough of teaching. And one result of his teaching was that I became a science writer. He made me fall in love with science as well. Not enough in love that I actually ended up doing it, but close enough. And so, so I want to thank the adult school for that great honor that you bestowed on him. He also would have been proud because of this series itself. He loved, as I say, learning about the universe. He loved teaching about the universe. And in this series, you are going to hear about many, many aspects of the natural world from the people. And this is, by the way, why I love being a science writer. When I was growing up, I would read about science in books and things like that. My father would tell me about it. But now I get to talk to the people who are actually doing it, who are actually doing not just science, but the most exciting, leading-edge science in every field that there is. Naturally, because if I talked to people who weren't doing that, it wouldn't appear in Time Magazine. So I get to talk to the most exciting scientists on the planet and write about them. You are going to learn about science and the natural world and technology from some of those same people in this series. So even if it snows, make them hold the thing. It's really going to be wonderful. And I've looked over the list. I'm not just saying this. I've looked over the list of speakers, and it's really going to be wonderful. And now I'm going to make a segue into my other introduction. I told you I write about the people doing the most exciting science in the world, and in 1992 or so, more or less, give or take a year, I was working on this book. And I first ran into Lyman Page, our speaker tonight, outside the Carnegie Center daycare facility across Route 1, where he was dropping off his son and I was dropping off my daughter. And I almost knocked him over when I found out what his name was, because I'd never met him before. I said, I've got to interview you. And people didn't usually do this at the daycare center. But I was working on this book about the Big Bang and the origin of the universe and cosmology, and people at Princeton told me, you got to talk to Lyman Page because he's really doing some exciting stuff. And what he was doing back then was what he was going to talk about tonight. He was observing the birth of the universe. And back then he was doing it with balloons that were floating above Antarctica. And, right? Was it balloons or was it ground-based? Ground-based and balloons. But in the intervening years, he's worked on a satellite called the WMAP satellite, I'm sure he's going to tell you about it, which has given us by far the most precise and exciting data about the birth of the universe that you've ever seen, you've ever heard about. I'm just going to, since I have this here anyway, I will tell you briefly that Lyman was an undergraduate at Bowdoin College, unless I got it wrong with the book. Bowdoin College, very interested in physics, but after college he wasn't quite sure what he wanted to do next, so he took a job in Antarctica, monitoring a cosmic ray experiment where, he told me at least, he stayed for 17 months, and pretty quickly he got the actual work part of the job down to 10 minutes a day, which left him a lot of time free for reading and playing cards and painting and fixing the shack that he was in when it threatened to blow apart. After he left Antarctica, he still didn't know what he wanted to do, so he bought a 30-foot sailboat, 32-foot, 30 feet, was it? Big sailboat. And he was going to sail to the South Pacific, and he was going to go through the Panama Canal. And he got down to the Caribbean, and a terrible storm caught him, and he lost his rudder. And he decided maybe, instead of going to the South Pacific, he was going to graduate school in physics. And he made his way to MIT, where, and I'm going to have to quote directly here, where he got a job as a technician and studied for the graduate record exam, and tried to persuade a guy named Ray Weiss, a physicist in that department, to let me in as a graduate student. And here he's, I quote Lyman saying, "I did okay, and Ray persuaded the department to let me in. He has a reputation for taking on the occasional oddball case, and I was it that year." So, and then he ended up giving the boat to a lobsterman in Maine. But I will stop now because I'm much more interested in hearing about Lyman's work from Lyman himself. I give you Lyman Page. One more thing before he starts playing with his beach ball. At the launch of the WMAP satellite in Florida several years ago, I went down to watch this rocket take off. And while we were hanging around waiting, a tall, older man, very energetic, very friendly, came up and shook my hand and he said, "I'm the real Lyman Page." So I guess this is Lyman Page Jr.
Well, thank you, Michael. I don't know what to do after that. So it's a great pleasure to be here talking with you, and especially for this series. I know Aaron, I knew Aaron really well. He was our neighbor when, not the son that we met over at Carnegie. When my next two boys were born, he built boats for them to play with in the tub and brought them down. And we talked together, and he just gave me lots of advice over my time here. So it's really special to be able to talk to you in this honor tonight. So I'm going to talk to you about the work that Michael spoke of, and about observing the birth of the universe, and what it means, and mostly how cosmologists think about the universe, right? Because we've learned a huge amount in the last decade. And so I want to give you a sense of that, and this is sort of an enigmatic title, and tell you what we mean by that, and give you some idea of what we can look forward to soon, learning more. What this picture is here is, it's not a beach ball like this, but this is actually this is a map of the whole sky. And I just want to introduce you to, this way of thinking about it, because we'll keep coming back. This is looking out at the sky, all around the sky. What we've done is, if you look through the center of this beach ball, this is that hair, so I'll tell you about it in a little while. Through the center here, and you looked out, and then you unrolled it, slapped it on a piece of paper, just like a map of the world. That's what you get. The difference with this map, and say the map of the world, is that these blue and red spots there are actually a picture of quantum fluctuations for when the universe was a billionth of a billionth of a billionth of a billionth of a second old. And and it turns out from that, everything, all the structure in the universe, all the galaxies, ultimately all the planets, all the clusters of galaxies came from. And that's the picture I want to fill out for you and explain how it comes about. So we can really think of this as, this is, for us this is a baby picture of the universe, or a fossil of the early universe is a slightly more scientific way of saying it. Okay, so let me just, we're talking about the universe, so I want to set the scale. We're talking about cosmology, right, these large structures. So how big is it? Well, of course, it's really, really big. It's the biggest thing around, right? So just to give you a scale, the sun is 8 light minutes away, right? It takes light 8 minutes to get to the sun. And, okay, so that's our nearest star. The next nearest star is about 4 light years away. So 8 light minutes to the sun, 4 light years to the next star. The center of the galaxy, and this is the Milky Way, the center of the galaxy is about 25,000 light years away. And this is a picture, taken from a satellite. And you say, well, how can we see our galaxy like that? It looks like we're outside of it, but that's not the way to think about it. It's just that if you think of the galaxy as a dinner plate, our galaxy as a dinner plate, we're just about 2/3 of the way out from the center, right? So this is looking back at it in light that highlights dust in our galaxy and emission from dust in our galaxy. So that's the center of the galaxy. And then to put this in the context of stars, in our galaxy, there are about 100 billion stars. So that number is going to come up again in a minute. It's a good number to remember. And to tie it to sort of everyday terms. So at the height of the internet era, right, Bill Gates was worth about $100 billion. So he had $1 for every star in the galaxy. So that's the size, and this is small for us. This is small. This gets in our. Those galaxies could possibly get in our way. This is a picture to put that in some perspective of the Hubble Ultra Deep Field. So this is so here's a picture of actually where it is. There's the Hubble telescope. I have a pointer here, circling the Earth and looking up at this spot in the sky. And this is just a piece of that. And the area of that is about a 50th the size of the full moon. And you look there, and these guys, they aren't stars. Each one of those is a galaxy with 100 billion stars in it. Okay, and this is a 50th of the full moon. And so there are many, many patches like that in the sky. And when you go and you can just count up the galaxies in that, and you say, how many galaxies are there, right, over the whole sky? And there are, you might expect, amazingly, 100 billion. Okay, so Bill Gates also has $1 for every galaxy in the universe, whichever way you want to look at it. Okay, and so when we talk about cosmology, we're looking at this scale and larger. It's actually even still a small scale for us. We generally look at this scale and larger. So, I think that gives you some. That should give you the sort of this basic outline of the scale. Right, it's absolutely the largest scale we can get to. Okay, so what do we see when we go and we observe these guys here, all these galaxies, and it turns out, and so this is just by way of giving you a feel of how we think about the sky. And this is what Hubble observed. If we look far enough away, so we don't want to get confused by galaxies that are nearby, that are just a couple 100,000 light years away. We want to look really far away. So we go and look at galaxies that are far away. Hubble found that the further away it is, the faster it's moving. Okay, so this is called Hubble's law. So here we are, us, And you can see you go some distance away here, and that little arrow is telling us how fast the galaxy is moving. You double the distance, and it's going twice as fast. Okay? You triple the distance, and it's going 3 times as fast. Okay, so that's great, and you might say, well, aren't we the center of the universe, right? Because everything's rushing away from us. And so, of course, we're special, but we're not that special. Because, let's imagine now, so this is called the Hubble's law, right? That you move, the recessional velocity of the galaxy is proportional to the distance. If we move to this neighbor here, if we just move to that guy, so we were now sitting at rest with respect to that guy, right? Well, of course we'd be at rest. That's our neighbor. And this guy is now moving back because we've moved there, so he's at rest. So now he's moving back. And so this guy sees the exact same Hubble law, right? Twice as far, twice as fast, twice as far, twice as fast. And so every person, every galaxy in this picture sees the Hubble law. Okay, so that takes a minute to get your head around, right? Because now everyone sees the universe expanding. Everyone sees it expanding the same way. And it's just because you can hop from galaxies to galaxies like that. And we should think about this is the way, and we'll come back to this in a minute. We shouldn't think about this as galaxies flying apart, like exploding into some empty space. That's not what you want to do. The way you want to think about this is that space between the galaxies is being made. That's what the evolution of these scales of the universe is. You actually are making space between the galaxies. And we'll get to the size business in a second. So it's the same small advantages. And what's a way to see how that can be true? And it's a common construction, right? Is if you can imagine you were on the surface of a balloon. Okay, and the balloon was blowing up. And you imagine you were an ant on the surface of a balloon. And first off, forget the fact that the surface of a balloon is 2 dimensions blowing up in 3 dimensions. We're going to put that aside for a minute. Just forget that. Just imagine yourself just constrained to the surface of a balloon. Well, if it's blowing up and you're an ant wandering around on there, no matter where you were on the balloon, you would see the same picture. You would see all other ants moving away from you. Right? No matter where on that surface you were, they'd all be going away. Okay, so everyone would have the same picture, and you would be making balloon, right, in between you. And the jump that we're going to make is that, whereas you can imagine the balloon, you say, well, the balloon's a very finite thing, right? But the universe is not finite. The universe is infinite. Let me give you a way to think about that, and in a minute here. And so, another way you might think of it as raisins in a raisin pudding in an oven, a really big oven, right? Is that an infinite raisin pudding? That it's just everything is expanding. Okay, it heats up, and it's all expanding no matter which raisin you're on. As long as you don't look at the edge of your cake or your pudding, right? You're fine. You all see the same picture. Okay, so that and we think of it as making pudding, making space. Okay. So that's the Hubble law, and that's how you want to think about it. And now we want to put that in the context of our space, of real space. So we're going to get away from this balloon picture. That's just a crutch, if you will, and think about the bigger picture. And we have to add one more thing, and that is that the speed of light is finite. And what that does, and this will introduce the terminology, is it sets a maximum radius out to which we see. It does 2 things. It does that. The second thing it does is that since light has to travel to us and it's moving at a finite velocity, as we look out, we see things when they were younger. So telescopes are like time machines. Okay? So we look out and we see things younger. And so when I say we, when cosmologists think about the universe, they think about it more or less like this. This blue is the universe. Okay? And it is infinite. It has always been infinite. It looks like it will always be infinite. Now those are we interpret the measurements as they are today. It's always been infinite. It'll always be infinite. When we talk about the observable universe and sometimes drop observable. It is this sphere around us set, the diameter is set by the finite speed of light. So if we know the universe is roughly 13 billion years old, it's a 13 billion light year diameter sphere. Okay. And so the objects that are moving furthest away from, the objects furthest away, we see when they're younger and younger and younger. Okay? So that's the picture. And to give you just one more perspective on that, imagine that you could somehow instantly be transported to the edge of our observable universe. You would look back and you would see the environment around us that eventually gave rise to us. Now, you wouldn't see us now. You'd see what's here long before the Earth and our galaxy formed. Okay, so that's the picture, and we'll keep adding to that and filling that out. Here is another version of it. This is a picture made by Mark Subarow and collaborators of the Sloan Digital Sky Survey. And these are wedges. This is led by Jim Gunn in our astronomy department. These are wedges of where they observe the sky. Each one of those objects is a galaxy, so you're flying out through their map. Mark has taken some little liberty in identifying the kinds of galaxies. Right? So those are where the galaxies are. This is a real map of the sky. That's not there, right? So you won't look up and find that. And this is where they've looked. And so they keep looking out. Those are nearby galaxies. These are called the luminous red galaxies, which are the next branch. So those are younger. You've seen them younger, and they're redder. And then here are these things called quasars, which you've seen, younger and further away. So we're looking back younger and younger and younger, and then we look out past all the galaxies, and we see the beach ball. Okay? We see this stuff called the cosmic microwave background. And the picture that we're going to put together here is that somehow these quantum fluctuations gave rise to these quantum fluctuations perturb the light that we look at here to make this picture. And these perturbations correspond to changes in the strength of gravity. And where gravity, if you will, was stronger, objects formed, all this stuff in between us here, and all the structure in the universe formed. So the picture is, this is this primordial soup out here, almost structureless. Structureless except for those hot and cold spots. We don't get to those. And as the universe evolves, right, going back is younger, so you can think of it as evolving in here, matter starts to fall into these places where gravity is stronger and form galaxies and clusters of galaxies. Okay, so let's put this slightly differently. Here then is our cosmic history, again from the Hubble Ultra Deep Field. The further out you go, if you go really far out, you can see this stuff. This is the surface of the beach ball called the cosmic microwave background. There a minute. And then as you come in here, you start forming structure like galaxies and clusters of galaxies that we see nearby us. Okay, so that seems pretty, well, maybe it seems far out, but it's a good picture, right? And it works, it works amazingly well. So let me try to get, I know this can be seem abstract. And so let me try to get just put take one more step to bring a little more towards science that we know a little better. It's actually some of this is happening up Route 1 there at Forstall. And then actually, I'll tell you how we measure it, and that will give you some feeling of this is like, we could all go out and be measuring this radiation and making these pictures. So the cosmic microwave background, the CMB, this beach ball of stuff that you're talking about, really is the light from the edge of the universe. And so how is it that it gets there? And so I said microwaves, and we'll observe it in microwave regime, and we'll also get to that in a minute. So the idea is that the universe, right, the birth of the universe, and again, the birth of the universe it's not in one place. It's everywhere, right? It's this hot, firing mess, right? And it's expanding. So it's infinite, it's always been expanding, and it looks like it always will now. So it expands from this really fiery beginning, and there is nothing at the start that we know about, that we can identify with things to do. And it cools, and then suddenly atoms or particles of protons, neutrons are made, electrons are made, there's light is actually made at some point, and it expands and cools and expands and cools. And it turns out that it expands and cools. In the first 3 minutes, all the nuclei of all the atoms that eventually turn into the stuff of which were made. And then it expands and cools, so it's a plasma. And so electrons aren't connected to the protons. Finally, it expands and cools so much that the Coulomb interaction, right, just the plus and minus opposite charges attract, is strong enough to capture the electrons and keep them from scattering light. And that's what I'm trying to depict here. So there's this transition when the universe gets cold enough, so we form atoms, and when you form atoms, they don't scatter light. And it's called the epoch of decoupling because the light decouples from the matter. And it happened, and this is what cosmology is, we're learning from cosmology, it happened 379,000 plus or minus 1,000 years after the Big Bang. So we're getting to know the universe like it's our own backyard. So this happened, and that happened, so that's really young, right? That's, well, not a billion to a billion to a billion second, but it's still young. And the light, since it could no longer interact with the matter, just free streamed to us from that time till now, not interacting with anything. And that's why when we look out in those pictures, when we look up at the sky, and then you can do this from Princeton, right? When you look up at the sky, you can see this surface around us that is literally light emitted from 379,000 years after the Big Bang. We're swimming in it. It's all around us. Okay, and so, why a fossil? Talked about that earlier. Is that these atoms here, these guys, flow in response to the gravitational landscape. And eventually, as I said before, go on to form galaxies and clusters of galaxies, right? So that is, when you see it, when you think about the Big Bang, it's just this sort of this mush of or at some point, just light and a few scattered nuclei around, right? And so we end up with Milky Ways and stars and Hubble Deep Field pictures and things like that. And what had to happen there is you needed places where gravity is stronger and gravity is weaker. And so if you think, you can think of a landscape. So actually, like mountains and valleys, in which where gravity is stronger, all the matter flows in and forms something like a galaxy. And so these hot and cold spots there on that sky, the red and the blue spots on that sky, which are really just variations in intensity in microwave emission, are to also trace out the gravitational landscape. Okay. So that's why we can make this connection between microwave emission and the background, the gravitational landscape that gave rise to all the structure of the universe. those variations that I just showed you are really tiny. When we look at this, and we see hot and cold spots, these are of, if you take the temperature of the universe and you ask how big are those variations that gave rise to all this structure, they're only about a part in 100,000. So these are tiny little deviations, if you will, in the background of the universe that gave rise to eventually all of us. Okay, so now to bring this more down to earth, speak. So how do we measure this, right? This is not, it's not mystery. This stuff was actually discovered up at Bell Labs by Penzias and Wilson, while the group here, Dickey, Peebles, Roland, Wilkinson, were actually looking for it. So of course those guys went off and got the Nobel Prize for it, and the group here kept on studying it and other things. But anyway, but how do we measure it? And this isn't quite what they did, but it's a modern version of it. So just to set the scale, when the microwave background gave this picture of this hot plasma early on, expanding and cooling, and when it cooled, it is cooled now with the expansion of the universe to a little below 3 degrees of absolute zero. Okay, or 2.725 degrees above absolute zero. And to give you some idea, it's about 1,000 times cooler than the sun. The sun's about 6,000 degrees. And so the sun, it's like the sun that's shining in the microwave regimes. And you have, in some sense, you've all already detected this. To give you a picture of it, well, if you turn to, say, channel 69, as long as you don't have cable, right, you have to have an antenna pointing towards the sky. If you turn to, say, and I don't even know if channel 69 has programming on it or not, just to turn to any inactive channel. Get the fuzz there. 1% of that fuzz comes from the microwave background, comes from the light left over from the Big Bang. And you can see it right away because the Earth emits radiation at 300 degrees Kelvin. The microwave background is about 3 Kelvin, and so it's 1% of that. That gives you the fuzz. So these experiments, these maps, what they're like, it's like we're just fancy TV repairmen, right? We build really good TVs and really good antennas, not like this one, but you could do it taking this antenna and pointing it around in the sky and measuring the change in fuzz on your TV. And that's what we do. I remember there was a graduate student here, Dave Cottingham, who wanted to make a CMB measuring device for everybody, and used, he got a coffee can and a Frisbee, and covered the Frisbee with aluminum foil, put the coffee can out there, and then tried to make some, it didn't quite work, so not quite, but tried to make some little receiver so we could all go measure the CMB. But that's the idea. So we've gotten a little fancier than that. I want to tell you briefly about this satellite that Michael spoke of. This is the guy who started it, close colleague certainly of me, a mentor, and a colleague of Aaron. This is Dave Wilkinson, who first came up with pushing this satellite, who died 3.5 years ago, but saw all the data. So in his honor, we call it the Wilkinson Microwave Anisotropy Probe. Here it is. This satellite is now, if I can get this to go. There's a picture from our colleagues at NASA. It's up there, orbiting, taking data as I speak. It is 2 fancy satellite dishes, back to back, right? You could take the ones out of your backyard almost, put them up in this place in space, point them to opposite sides, and there are 2 of them, right? One points up here, and one points down there. And this thing is up there, measuring the microwave background all the time. And the reason there are 2 of them, right, is since we're looking for fluctuations, right? Because it's the fluctuations in this gravitational landscape that give rise to all the structure and have all the clues in it. We want to look at differences in temperature across the sky. So we just look at differences from 2 spots in the sky. And actually a good chunk of this was built right down the street here in Javelin. So here's the crew who put it together and has been thinking about it. Here's where it is. WMAP is actually, we launched it in 2001. It's now, took a 3-month trip out to the second Lagrange point, which is actually orbits the sun, right? It doesn't orbit the Earth. It's about 4 times further away than the moon. We're our own little planet out there, right? Orbiting around the sun, taking data, following something like this. So this is the satellite with our 2 microwave receivers just spinning around. And this, the red and the blue are both sides, right? Because we always want to make these differences. And in about 1 hour, this is sped up to show you what 1 hour coverage looks like. We cover about 1/3 of the sky. And it just sits up there doing it. It's like one of those Etch-a-Sketch patterns, right? And it just sits up there doing it. It's been doing it for 4 years now, taking data. So we take all those different measurements that get telemetered down to us, and we combine them, and we get this map, which is slightly different than the one I started with. And let me just explain why. The first one didn't have any galaxy in it. Just like I showed you that picture from the Derby satellite, the image of our galaxy. We see the same thing in the microwave. So this is like, that red swath right there is us looking through the galaxy. And the rest of this stuff is these hot and cold spots that we see just peppered throughout the sky. You know, it's like one of my colleagues, Dave Spergel, grew up in Queens. So he said, you know, looking at the galaxy here is like living in Queens and looking in Manhattan, right? So there's a whole bunch of stuff going on over there, but even though you're in New York City, right, you still see the galaxy, you see all these things wrapped around you. So this is from the galaxy here. And it's just like moving that TV receiver all over the sky. We measure that the sky is slightly hotter there, slightly colder, and from the bluest blue to the reddest red, to give you a scale, is about 400 millionths of a degree. So, and when I say it's a part in 100,000, it means that actually the temperature of the universe is about 3 degrees above absolute zero. And these hot and cold spots here, where the intensity varies, is about a part in 100,000 of that. Okay, what we do is we zoom in. We have lots of resolution. We can zoom in on a little bit of that. We can even zoom in more. And this is just for scale. This is 5 degrees. And you can look at that, and you can. This is just a random pattern it's random. It's our pattern, right? We measure it once. Everyone from now on will measure nearly the same thing. But there is a pattern on the sky, and you can see that it's clumped up. If you were to squint your eyes and look at that, you would say there's some characteristic size, red and blue spots of, what would you say? Anybody? How many degrees? A couple? 3, 2-ish, maybe even 1, somewhere in there, right? It's not a lot of fine scale structure, and it's not half red and half blue, right? It's got there's some scale associated with it. And so where does that scale come from? Why do we get that? And it's, again, here is this picture of the gravitational potential that we can, of the gravitational landscape, which we can show as hills and valleys. The blue dots here are actually the plasma, the light, matter, light mixed together that's falling into the valleys, like fog on a cold night, right? You go down, you ride your bike through a valley, it's colder down there, it's like fog rolling into the valleys, rolling out of these. And we get hot and cold spots because if we look, it's because this stuff travels, it takes some time to travel over that period. And if we look, we take the age of the universe at decoupling, 379,000 years, we ask how fast this stuff can travel in that time. If you have a big gravitational well, that just sets the scale. And it turns out that that's 1 degree. In the age of the universe, before the time when the light is free to roam, the plasma, that early universe plasma can travel 1 degree. So it settles into the valleys on about that scale. And this is actually a plot that was on the front page of the New York Times, so I know it's safe to show to everyone. And, right, anyway, so here is the picture then, is that we get, and we can just ignore those right now. This is the amount of fluctuation power, the amount of the intensity of hot and cold spots. And you can see that it's maximum at 1 degree. So I wanted to show here. And this is, again, a picture of the plasma falling into a gravitational potential well. And a neat thing here, to give you some idea of how well we're knowing the universe, these points here are all the data with error bars, and that's a model based on just 5 cosmological parameters. We can actually, so we'll get to in a minute, with just a few cosmological parameters, we can explain millions, literally millions of observations. So that's the picture I want to give you. So here's a bit of, so we have, just to review, right? We have this picture of this gravitational landscape, somehow given to us from the birth of the universe, from very early on. Whatever was present early on gave us this gravitational landscape. The matter falls into it. The universe becomes transparent, and we get a picture of the sky, right? That moment of decoupling, we get a picture of the sky, and now we're going to start to look at it to see what we can find out. And we call this the fundamental mode, that one I showed you, those 1 degree splotches. And if you will, that acts like a footprint or a yardstick at the edge of the observable universe. And the reason is because we can calculate how big these spots are. Just on pen and paper, using physics that was from the 1800s. You can just go down and say, that spot has to be this many miles across. We don't use miles, but it has to be this big apart. And then we can just go, and we can measure how big it is. And this is now one of the better measured numbers in cosmology, is we can measure the average size of those spots is about 0.6 degrees. And so we can then get the size of the observable universe, and then from that standard yardstick, we can get really the distance across the universe. And knowing the distance and the speed of light, we can find that the universe is 13.7 plus or minus 0.2 billion years old. This is another picture of the types of just things that you can figure out from thinking about this radiation. And that is, we know the age of the universe to within the age the dinosaurs roamed the Earth, right? To within 200 million years. So this is getting to be a familiar, our Hubble patch, if you will, is it's a familiar place. Okay, so we can learn much more than that. And we talked about this model here. Here's again the data with error bars. And here are, let me just take a minute here to tell you the rest. What's actually going on here in those other bumps and limits. Right? Remember, this is inverse angular scale, so that's a degree. That's about 90 degrees, 180 degrees. That is the size of the full moon, right there. And so that's where all the fluctuation power is. It turns out if you look really hard in that map, you can see these subsidiary bumps. And again, it's just from like this one, right there, is from that plasma early on in the universe. Not only, so the biggest fluctuation there is the plasma falling into a gravitational potential well once. The other ones are from plasma over half the distance, falling in once and coming back. The next bump is from plasma on the third of the distance, falling in once, back, and back in. We can actually go and we can see all those. Right? So we're really getting, the picture really is holding together well. And it turns out that from these, we can tell the amount of baryons in the universe. Because, as you can imagine, since we can compute all this stuff with physics from the 1800s, right, and just to tell you, baryons, sorry for the jargon, baryons are the stuff of which we're made, right? So baryons are, for all intents and purposes, just protons and neutrons, the stuff of which everything we're familiar is made. You can compute then that the ratio of that, it turns out the ratio of that peak to that peak is directly, from that ratio you can read off the amount of baryons in the universe. And what we do, and you'll see some of this terminology around, is we use omega to tell us the fraction of the universe in a certain component. So we can look at this, we can just look at this plot and say that the fraction of the universe in baryons is about 4.4%, that's an amazing thing. It means that the stuff of which we're familiar is only, of which we have all of our experience, right, which we've looked at the sky in for however long humankind's been around, is only 4.4% of the universe. It's like the new Copernican revolution, right? Not only are we not the center, the stuff of which we're made isn't even what most of the universe is made of. So there's another component in here that we can get from this radiation. And as I said, there are other attacks, there are other approaches to figuring these things out. And that is the overall matter density of the universe. And it turns out, again from this radiation, and actually mostly from comparing that peak to that peak and that peak to this general area, it turns out that we can tell that the net matter content has to be more than the baryon content. So here we are in the universe. We know we're not made of, the stuff of which we're made doesn't comprise most of it, but there's a whole bunch more matter out there. And we know it's not baryons. It's actually called cold dark matter. It's called cold because it's not moving around much, and dark because it doesn't interact with light. It just interacts with gravity, and it responds gravitationally. And the CERN, the Large Hadron Collider in CERN, hopes to find possible candidates for that. So that's 27%. So actually the weird stuff, the new stuff, the matter, that would be 27 minus 5, or 22%, 23%. So we have 4% of the stuff of which we're made, 23% of this new kind of matter, which we have no direct experience with, but we hope to see in particle physics experiments that will start the next, we'll get results from the next 5 years. And then there is this completely new term called dark matter. There's 22.6. C is for cold dark matter. Then we see that there's this whole new term, which we have here as the cosmological constant, which is yet, and I'll talk about it in a minute, yet something completely different and new to us. So here's the picture we get from studying this radiation. That the universe, and there are a few other parameters that we measure, but that the universe is comprised of something like 73% is dark energy, or this cosmological constant, 4% atoms, and 23% is dark matter. And the thing to take away from here is this isn't just fanciful. This is measuring the sky here and fitting these models together. I mean, this is really precise data, right? And this is where cosmology is these days. Okay, so let me come to a close here by giving you the sort of abbreviated standard model of cosmology. And that is, and so relating back to where we started, so very early on, and this is in that billionth of a second, some quantum field, and we don't know what it is, but it impressed on the universe this gravitational landscape. And this is just a little piece from it, of taken out of that map I showed you. And it is, if you imagine a quantum field is just this whirling field of literally quantum fluctuations, right? Tiny fractions of the size of the atom. So this field is imposed. The universe expands so fast and so much early on that fluctuations that are a tiny fraction the diameter of a proton are spread out and writ across the sky as fluctuations in gravitational potential. All the matter that's then formed in the universe falls into those changes, variations in gravitational potential, and then comes back to eventually, say, produce us. But of that matter, as I said, only about 1/6 of it is the kind that we're used to. So, and when I say, just again to relate to the title here, talking about observing the birth of the universe, we are literally now in the next stage of measuring the properties of this field. We can measure the properties of the exact fluctuation pattern. We can see even if there are gravitational waves traversing us, traversing the universe, and those will give us another handle on this universe, this billionth second of the universe. And it's all from studying this radiation. And now, as we got to in this last slide, so we have this picture here, and it really hangs together. We've got this new term, so we've got the dark matter we don't know. We've got this new term here called the dark energy, which is, we have to have it in the models, but it's a weird thing, and I'll get to it. I'll explain it in a minute. So here is the status of this model. It is constrained, this picture I told you about is constrained at the few percent level. Okay? I mean, this model is better understood in some sense than some measurements of elementary particles. There are no significant observations that are in conflict with the model, and there are a lot of measurements. And it's not like, we're experimentalists, we're observers, we're contrarians, right? We want to find the thing that disagrees, and we're always looking for it. And we keep thinking we'll find something, but really, so far, there's nothing wrong with this. And this includes measurements from the Hubble Space Telescope. It includes measurements, every telescope you've ever heard of, every around the world, measurements from balloons, from the ground, of the microwave background. They all agree with this. And there are measurements, you can look in the intervening space. This model agrees with completely independent measurements of hydrogen, helium, and lithium. The same, so you can take the microwave background, right? This light from the edge of the universe, compute how much helium there should be in the universe. I mean, not even looking at anything nearby. And then go to the Hubble Space Telescope and ask about some stars nearby, some galaxies nearby, compute what you should, the amount of helium, and get the same answer. Right? It's just amazing. So the model is really tight, and we're all really excited, but the big problem is this model is really strange. And the problem is why it's great science. It's why it's what keeps us working late at night. It's strange in that there are just new mysteries out there. Probably the biggest one is, even though we don't know what this dark matter is, we're sort of convinced we'll find it. In some ways, there are experiments around the world trying to find it. But this dark energy is, or cosmological constant, or goes by the name of quintessence in some cases. It has no foundation in any fundamental theory of nature that we have. It is a whole new thing. And to give you some, and it just means either, probably I think most of the money now is on it. It means we don't understand gravity. We don't understand how forces are unified at a very deep level. And how does this act? And so leave you with this, is it really, it looks like the universe it looks like the vacuum, take the vacuum, has some energy density associated with it. that is actually driving the universe apart. It's causing it to accelerate. So that Hubble law that I showed you, those galaxies eventually will start to all accelerate. They're accelerating away from us now. We look far enough away. And you go out another 13, 15 billion years or 100 billion years, we'll see these guys accelerating away. So ultimately, after a long time, we'll be the only galaxy around. We won't get those nice pictures from the Hubble. And so it's almost like an anti-gravity blowing the universe apart. And as I said, we don't know how to think about it. We're trying to measure different properties of it, and just trying to understand this picture. So this is, again, I'll come back to this was first seen with the supernova data in some sense, and really seeing the best measurements of it are with this with the microwave background. But it's what keeps now physicists of all kinds of brilliant guys at the Institute are thinking about this. Keeps observers looking for, trying to figure out how to get a handle on it. What can we do? What can we measure in the sky to understand this strange energy better? And so it's wonderful that we know the universe so well, but it's also it's still exciting because it's so new and so strange to us. So let me end there. That picture I started with. Thank you. So, questions?
What are the experiments you hope for?
Okay, so there are many. One, so the sorts of. Sure, thank you. Yeah, so these are what are the experiments that we hope for. Let me just give you. Well, I can do it from here. One that a number of different groups around the country are working on is this map is made with a resolution of about half the full moon. We're working on doing the same sorts of maps over a fraction of this with a resolution of about a tenth the full moon. And it turns out that with that, we can, let me go back here a few pictures. With that, right, this is finer angular resolution on this plot is that way. It turns out that we can expand the baseline to that plot. And then it turns out that with that expanded baseline, it tells us one of the key parameters of the field theories at 10 to the minus 35 seconds. And I skirted around the words because I didn't want to confuse things. There's this model of the universe called inflation that gives rise to this, that gave rise to this incredible expansion early on that blew apart these quantum fluctuations and spread them across the sky. And this is from the mid-'80s. And the amazing, this is a model that just wasn't around. It wasn't around 30 years ago. This is a model based on real physics we know and love, and it makes a prediction for what the radiation should, if you compare the radiation out here to here, what it should look like. And so we're trying to build experiments to measure that. So it's called the scalar spectral index. We're trying to find deviations from unity of the scalar spectral index. And that's something that just directly tells us, just absolutely maps directly on the universe at 10 to the minus 35 seconds. Another one is where a group of us, or a number of groups, talking about building a satellite, because it turns out if there were gravitational waves in the universe, that they affect the microwave background polarization. So now we're not talking about temperature, actually polarization. So if you had microwave eyes, Polaroid glasses, microwave eyes, you can see that this stuff is polarized. And we're looking for these gravitational waves, Einstein's gravitational waves, traverse the universe. They squeeze it this way and expand it this way. So these are gravitational waves with wavelengths the size of the universe. And it turns out that we can detect things like the squeezing of the universe by light years over the size of the universe, by a few light years. So we'll go on and look for things like that. So there, and again, then we can relate that directly to these field theories of the early universe. Sorry, still saying.
What's the current theory as to where we are in this birthing process of the universe? Are we still very near the very beginning? Or
Okay, so the question was, where are we in this whole process? And there are, it goes, so just some perspective. This is a really, what I've shown you as a really pretty well-tested picture, models and well-motivated theories. And there are a lot of new theories coming out. I can just throw one out. The baseline, this nominal picture was there was this inflation process that happened early in the universe. There's this dark energy, but we don't know where it came from, and the universe will just accelerate and will end cold and dark. Okay. Another one, and that's if you just ran things on, is with the context we have now in our favorite model. Other people, most notably Paul Steinhardt, Neil Turok, Bert Overhoek and colleagues, have a model that they're still refining, where the universe actually, this is just one cycle of the universe that's expanding, and then using some heavy artillery from string theory, right? It expands and it's blown apart and then starts again, and expands and goes and expands and goes. So it's a cyclic model. And one of the neat things about a cyclic model is it predicts there should be none of these gravitational waves that are traversing the universe. So if we find them, we'll eliminate that. So, or yes, we can't prove it. We can only disprove it, unfortunately. But so in that picture, right, we are somewhere in a long continuum, and then these folks argue over, well, maybe it went awry 10 cycles ago, or it'll go awry 10 cycles, and it's hard to tell. I mean, once you get out of the realm of really making firm predictions, it's difficult. The nice thing about this stuff so far is they're really clear predictions.
You discussed gravitational waves a moment ago showing coming and going, but that implies or compression and non-compression. That's an antagonist. I didn't hear where the other half of the wave came from.
Okay, so in this, the question was, I think, how should we really think about gravitational waves traversing the universe, and where the other half of the wave comes from? Let me go back to, it doesn't foul me up here. One more. Here we go. Okay, in this picture, we can think of, because we can think of these perturbations or gravitational waves, right? The perturbations from background as traversing this whole space here. So our universe, our observable universe, just picks out a piece of them. So this wave, let's say it's propagating like this, and it does propagate, right? It travels it can travel at the speed of light. Of course, it's going to squeeze space like this and expand it like this. And it's going to go that way. And there'll be another one going that way. And we're just in the middle of a sea of gravitational waves that are traversing the universe, expanding space this way, and contracting it this way, and expanding it this way. And so that's I think the picture is that we're just, we're an ice cream scoop out of a 5-gallon bucket of universe, right? And these processes are all going on around us, and then we see a bit of them as they come through our universe. And you can imagine, right? This is the edge of the ice cream scoop, right? So they're going to do things to this that we see. And maybe to give you some other maybe another handle on this, right? In this picture here, if we if we could wait another, probably 1,000, if we waited 1,000 years for the universe to expand a little bit, it looks like, if we make rough numbers, that we could actually perceptibly look for the change in pattern on the sky of what you see on the beach ball. And that's because in this picture here, right, as this moves out, it's sampling different gravitational landscape. And so you actually, as this moves out, it's very difficult to measure the cooling rate of the universe. But as this moves out, you actually see different fluctuations. You're sampling new parts of the universe. So that pattern changes. I don't know if that helps.
Thank you.
Please.
I may be remembering wrong, but I thought people used to say that the universe at the beginning was the size of a pinhead and then it was the size of a beach ball and so forth, and it expanded beyond that. You said that the universe is an infinite size even at the very beginning.
Yeah, you have to be, I like saying the infinite size just, well, it is as far as everything we know, because it takes you away from this notion of something exploding in space, which is just the wrong picture. The size of the pin or the beach ball, you can relate that to, say, the causal size, right? How far light has traveled in a given amount of time. Right? Because you could, so this, going back in time, was everything was much smaller. But you can come up with, right, you just take some approximation, just take the age of the universe times the speed of light, and that's how big your observable universe is. That just gets smaller and smaller.
So the observable universe is tiny, but the actual universe is infinite.
Yeah.
Even at the beginning.
Yeah. And the picture is, I mean, people now, even actually with these data that I showed you, they look, there are completely well-posed scientific questions of, what is this space out here like? Can it wrap back on itself? Can it have is there some funny topology to it? Does it look like a torus of which we're just sampling a tiny bit, right? And you can make predictions from those other thoughts and test them with these data, because this is the beach ball, right? It's the edge of the universe, the edge of the observable universe. And you can see that, you can tell that there's sort of nothing funny going on with our model up to something like twice the diameter of the observable universe now, right? Space can't be warped in some peculiar way.
Could there be some other observable universe that others are observing elsewhere in the infinity?
Yeah, so or right over here, right? So the pictures right now, if you were to go out, so the question was, could there be some other observable universe really far away that could be just like us or completely different? And certainly in this simple model, right? And again, this is you have to put this in the framework of the model, because if you can't test it, you're not really going to you're not going to get some observer or some experimentalist to believe it. But the model that hangs together is that you could be somebody over here with their observable universe that size it would be just like ours. They'd see the same things, we just have nothing in common, right? So I should say nothing in common. The one thing we have in common is that we would measure the same microwave background. And that's the thing. But there are models now coming out of string theory that say there could be multiverses, and some of them have just completely different laws of physics, but we don't even sample them. But I think that's, again, I think probably because it's just like, what's really amazing is that these questions out there that there's some fanciful ones, I think, like that, or they're different string vacua or some such thing. And who knows if we'll ever be able to test them. But the really amazing things is there are real predictions for how the universe is, and that we can tell so much of it. I think that's the measuring and testing. I really try to stick to those.
How can you, with the same breath, almost say that the universe is a certain dimension, 13.43 billion light years radius, and also say that it is infinite, because that's contradictory.
That's okay. That's this. That's, if you, so it's 13.7 billion years old. So sorry again, how big is the, how can you just talk about something like the finite size and how should you think about it in this context? It's 13.7 billion years old, so roughly it's 13.7 billion light years across. It's the part we see. But there's, and that's the word we throw around, it's a Hubble patch. Right? It's our neighborhood in this bigger picture.
It's extending well beyond what we can see.
Yes. Yes.
So when it all contracts down,
There's not enough, so it's not going to contract. There's not enough matter in the universe to make it contract. And if anything, this dark energy is just going to blow it apart.
The 13.7 is calculated from our current ability to measure, right?
Yes.
Because, I mean, our observable universe is longer ago in history than it was 500 years ago.
Yeah.
Based
So
on the ability to measure, so does that mean that 500 years from now, we'll have a different number?
So the question is how well do we know and how do we think about that 13.7 billion years? The error bar is 200 million years. So we will know, and I'll tell you, the error bar will get down to about probably 50 million years. And so in 50 million, in 50 million years, we would say the universe is 13.75 billion years old.
I didn't take the prerequisite, so. But I'm still trying to get a handle on our ability to measure, first with the naked eye, and then it was with improved methods
Right.
of seeing light, and now it's microwave
Right.
that we're measuring. How do we know we're not measuring? How do we know we're measuring as far as we can?
Okay, because, so how do we know that we're really, why isn't this all just smoke and mirrors, right? Why do if we keep looking at these different wavelengths and we somehow look back further, how do we know there isn't, we don't look back some other way that we look back further, right? Do I have that right? Okay, so the picture is that we can, this picture here, we can compute when this happened to within 1,000 years. Because in the statement here that we know and this is the amazing thing that happens, is we know the physics of the universe that well. And because we can, I mean, you see these just qualitatively, right? So that one. I mean, this isn't just any, I mean, these are tiny error bars. I mean, these are really precise measurements of many, many measurements at the fraction of a percent level of this radiation across the sky. And it's not just any model that can fit those. And you really, I mean, we know that peak isn't down there. And so, yes, there are probably elements of this model that we don't have right. But the big picture is looking really solid. So that's, I think, the quick thing. We know when this happened.
What was the radius of our universe 13.7 billion years ago?
What was the radius of our universe 13.7 billion years ago? So the radius of the observable universe.
The universe that we're familiar with, yeah.
Yeah, it was.
Was it the size of a
If it was-
basketball, or was it
Yes.
28 billion?
No, size of a baseball. But.
And you're saying that this is the image, whatever it was 13.7 billion years ago, that image of the universe just spread out is what we're looking at?
Yes, except we see it through light, and so we see it this 379,000 years, because that's when this light was released to get to us. Right. So here, let me tell you another way. We can, from here, we can look at the sun, which is a nice. It's. I think just looking at our sun is a good way to think about it, because the sun has a surface, right? We see the surface. We know if we go past that surface, it's going to get hotter inside as we go towards the center. It's like having the sun, if you will, wrapped around us and cooled way down. I don't know if that helps or hurts, but it's like a photosphere. And so that's again, this picture is just cooled off. So the universe was indeed smaller. There was this plasma. We didn't see this at 13.7 billion years ago, because if you go back long enough, there wasn't light.
Right, but 13.7 billion years ago, was the physical size of the universe the size of a baseball, or was it?
Yeah, it was
billions of miles apart.
When it was. When the universe was 8 minutes old, it was roughly the size of the distance between here to the sun. 8 light minutes. And everything in there is with us now.
But what you're looking at with this map is that image, but that many years ago.
Yeah, a great approximation. So all that stuff happened and is spread out. And it's just, space has been made, and that thing is in there.
But if the gravitational waves transverse this system, they must be not part of it.
No, okay, so that's what, so the question is, say, is something like gravitational waves traverse this, they must not be part of it. And they may, and this is this piece of this model, this mechanism called inflation does, is it takes whatever field you have at a billion, 10 to the minus 35 seconds, billion, and actually takes it and spreads it out, it expands it superluminally. And that's why, that blue swath, that's why I can tell you that even if you're outside of our Hubble patch, you have to measure the same temperature of the microwave background. So it takes all that field and expands it superluminally outward. And then that happens, inflation ends, and we're like this little, we start out as, our horizon starts out as some tiny little piece in this background that's been laid out. And the background is many times our size. And it's in that background that those gravitational waves are moving. And then really all these fluctuations we see these hot and cold spots are right, these are sampling the gravitational landscape of that background. So it really is, it's like
faster than the speed of light then?
Very early on, there was a superluminal period that took us faster than the speed of that ripped things apart. And you asked about these inflation questions. So, and you can tell it has to exist you can tell that we needed some mechanism like that. Because just look at our universe now. If you look at that side of it, it's one temperature. You look at that side of it, and it's the same temperature to within a part in 100,000. And yet, that side of the universe, you go all the way to the edge, hasn't had time to talk to that side of the universe. Right? We're in the middle. We can have light get from here to us and there to us, but it can't have gotten from there to there. Right? And so we know there had to be some process early on, and this is called inflation, that linked all those scales together. And that's where these gravitational waves came from. And that's why if we find them, we can actually say we're probing that 10 to the minus 35 seconds.
Take physics 102 next. Thank you very much.
Sure, please come on. Sure.